So I just wanted to finish up with chapter 11 in this really short video because we almost got there in class. So related to what I want to talk about is the idea that if you have a piece of wire that carries a current and you put it in a magnetic field, it feels a force. And so the expression that we see in our book and in class is the force is found through the cross product of the length of the wire, which has the direction that's the same as the current, crossed with a magnetic field. So what we did was we looked at some scenarios where we had a piece of wire or a loop of wire that was in a magnetic field. So for instance, I could have a wire with current traveling around in this counterclockwise direction. And when I placed it in a magnetic field, say like this, here's B. In that scenario, I had a force that went into the page on the right-hand side, no force on the top and the bottom because the current is either parallel or anti-parallel to the magnetic field. And then on the left-hand side, the force was out of the page. And so it was really easy for us to understand that that would produce a torque in that scenario. Now we had another scenario where we had a magnetic field, let's say, out of the page, and then we had a loop of wire in that magnetic field. Let's just let it go the same direction, just for kicks. And that's the direction of I. This is the direction of B. And when we look at the force in this scenario, so we found the force on the right-hand side. If I do I cross B, I get a force to the right. That means the force on the other side's to the left. Force up on the top, force down on the bottom. And so we see no torque. So we can see that the situation of how the wire loop will feel, like whether or not it has a torque, is going to be dependent on how the loop itself is oriented to the magnetic field. And to be honest, in these two cases, I basically showed you the two extremes where we see sort of the maximum torque produced if our loop is the plane of the loop is in the plane of the magnetic field. And in the second case, we saw that if the magnetic field is perpendicular to the plane of the loop, we feel no torque. So the idea is that we can conclude is that in other situations that are some mixture of this, I'll feel a torque, but not as strong. So let's try to look at where things are a little bit different. So the idea here is I have a loop of wire, and so the idea is that it has a particular width and it has a particular length. But now what we're doing is, if we're looking at it, our viewpoint of looking at this wire to sort of understand how the picture up above corresponds to my picture below is the idea that I would be sort of standing down here and looking at the wire from that viewpoint so that you can see that here we have the current going into the page and the other side of the wire is coming out at me right there. Now, so those two signs, if we did the I cross B for, say, the right-hand side, IL cross B gives the force, and we would find a force like there. And if we do it on the left-hand side, we find the force, of course, is in the opposite direction. So now the magnitude of that force, IL cross B, is just ILB, because that current in that piece is actually going to be perpendicular to that magnetic field, as you can see, because the current is either in or out of the page and the magnetic field is to the right. Now, we want to introduce the idea of torque. Torque is equal to RF sine theta, where theta is the angle between the radius vector and the force vector. Now, if we take our pivot point as the very center of the loop, our R for both forces, R is equal to the width over 2. It's half the width. And then the angle between them, you can see shown, the angle between the radius vector and the force vector is that angle theta that's shown on the diagram. So the torque would be, for one force, would be W over 2 times ILB, so that's the force, and then times the sine of theta. So that is like the force on the right-hand side. And then we have the force on the left-hand side, which produces exactly the same contribution. And so the total torque is going to be equal to, if I add W over 2 and W over 2, I get W, so it's WILB sine of theta, but W times L is just the area of the loop. And so it turns out that we can express the torque in a cross product form as IA cross with B, where A is the area of the loop ends up to have a vector nature. And let's look at how we determine its. So I had a little more room. So here's a picture where we're talking about the area vector. And so we use, again, a simple right-hand rule to find the direction of the area. Again, just to remind you, the idea that we're saying is the torque is the current times the area of the loop crossed with the magnetic field. Now, what they're trying to show you here, of course, keeping in mind how we defined area in the past, it's still very similar. The actual area enclosed by the loop would be a plane, but the area vector is going to be perpendicular to that. And the way that we decide which way it points is we wrap our fingers around in the way that the current is flowing. So here we're wrapping our fingers around like this. And then the way our thumb points is the direction of the area vector. We actually, you can see, they sometimes define the product of the area vector and the current as mu, and they call it the magnetic moment. And then in those cases, we define the torque as mu cross B. So in any case, that kind of wraps up what I wanted to cover. And so the idea being, of course, that if you have a wire loop that has a current flowing in it and you place it in a magnetic field, it will feel a torque and it will begin to rotate because of that torque. That is actually used in applications for both motors and for generating electricity at a very simple, from a very simple standpoint. All right, so I didn't think it was too much to finish this up. And now we'll be ready to move on to Chapter 12.